Hi guys, this is Miss Gold. Today's lesson is Module 4, Lesson 1%. Your outcomes for today's lesson are students understand that p% is the number p divided by 100 and that the symbol shown here means percent. Students convert between a fraction, decimal, and percent, including percents that are less than 1% or greater than 100. Students understand that the whole is 100% and use the formula part equals percent times whole to problem solve when given two terms out of the three from the part, whole, and percent. Students solve word problems involving percent using expressions, equations, and numeric and visual models, and students write a non-whole number percent as a complex fraction. The first thing I'd like you to do is to pause the video and complete the opening exercise, which is a matching exercise. When you're ready to continue, unpause the video and check over your answers. Okay, so I'd like you to check over your answers from the opening exercise. Notice that the lines connect the percentage to the correct worded statement. So for example, the 25%, I am half of a half. 5 cubic inches of water filled in a 20 cubic inch bottle. So notice that if we took 5 and divided by 20, you'd get 0.25, and that turned into percent is 25%. Let's take a look at example 1. Use the definition of the word percent to write each percent as a fraction and then a decimal. Now, percentages are the part out of the whole, and the whole being 100%. So when we come up with the fraction for this, you're really looking at the number that you're given out of 100. So here we would have 37.5 out of 100. But we tend to not like to see decimals in fractions. So what I'd like to do is multiply both the top and bottom by 10. That will help to move this decimal over 1. And so this gives me 375 out of 1,000. Now, as a decimal, if you take 375 divided by 1,000, you will get 0.375. And I want you to compare this to the original percent. Notice here, our decimal on this one is in between the 0 and the 3. But over here, it's in between the 7 and the 5. So the effect that it had of turning a percent into a decimal is it actually moved it over twice. And that's the effect of dividing essentially by 100. So the next one, we have 100. This would be 100 divided by 100. And notice 100 divided by 100 is actually equal to 1 over 1, which as a decimal would actually be 1.0. 110 would be 110 over 100. Now in this case, the top number is greater than the bottom number. So we should get a number that's greater than 1 when we divide these two. So if we take our calculators and do 110 divided by 100, you will get 1.1. Notice that both 100% and 110% are following the pattern we saw when turning a percent into a decimal for our first example here of moving the decimal over twice. So my decimal on this one is here, so I move it over 2 times and I get 1. Here I move it over 2 times and I get 1.1. The next one, we have 1 out of 100. And when we divide this, we get 1/100th as a decimal, so 0.01. Again, still following that pattern. The decimal would be here, so I'd have to move it once over the 1 and then move it over again, so we'd fill in a 0 here. 1/2, I probably want to turn this into a decimal to begin with, so this would be 0.5 over 100. But again, we don't like to see those decimals, so I'm going to multiply both top and bottom by 10 to move it over once, and that's going to give us 5 over 1,000. And so this decimal would be 5 thousandths. Again, following the pattern, when you turn this into a decimal, this would be 0.5%. And so I move it over twice, and you will get the 2 zeros after your decimal place. Notice that all of these decimals were created by taking percent is equal to part divided by whole. If I take the whole, it's being divided. What if I multiply both sides by the whole? Over here, our wholes would cancel, and we'd be left with just part. And over here, we'd be left with whole times percent, which we could also do the commutative property to rearrange as percent times whole. And so I get the formula percent times whole equals part, which is what we have right here. So this formula is really derived just from the basic idea of percent being part divided by whole. It's just rearranging the equation. And we're going to use this quite a bit in solving percentage problems. Example 2 says, in Ty's math class, 20% of students earned an A on a test. If there were 30 students in the class, how many got an A? I want to start by showing you how to solve this problem using a bar model. So when we were talking about percentages, 100% would be the entire bar, and then when I'm looking at a certain percentage of it, I'm looking at a part of the bar. So in this case, I make a bar, and I know that there are 30 students in the class. So that tells me that the value of this entire bar is 30. Now what I'm trying to find is 20% of the students. So if I want to find 20%, I need to know how many 20s are in 100. So if we take 100 and divide it by 20, we would get 5. So that's going to tell me to break my bar into 5 pieces. So when I divide it into 5 pieces, that tells me that each one of these pieces represents 20% of the bar. So if they are 5 equal pieces, then I can take my 30 and divide it by 5. And that tells me that each one of the pieces is worth 6. So if I'm just looking for 20%, that answer would be 6. So there are 6 students that earned an A on the test. So this is really our way to look at it in terms of a bar model. The second way to look at it is to create an algebraic model, and essentially what you're doing is you're translating word for word. So I want to highlight some important information. We know that 20% of the students earned an A, and that is going to help to determine our algebraic model. So what I'm going to do is write that statement down here, 20% of students earned an A. So if I translate word for word here, 20% needs to be turned into a decimal in order for us to work with it. So 20%, I'm going to move the decimal over twice, and this would be 0.20. Of in math, as we've talked about quite a bit, means to multiply, so of becomes multiplication. And then the total number of students, when they're saying students, they're implying the entire class, we know in this case is 30. And that would be equivalent to our unknown value of the number of students that earned an A. So here I have an algebraic model for 2 reasons. 1, we've created an equation, and it also involves a variable. So that follows the definition of an algebraic model. So the only thing I need to do here is solve, so I'm going to multiply 0.20 times 30, and that gives me 6, which is not surprising. It's what we saw in our bar model, and so we should see that connection there. We come to the same conclusion that 6 students earned an A on the test. Now, it's very helpful to know both of these versions and make sure that you use the one that you're comfortable with. I will say that in some cases, the bar model is not going to be a very friendly version to use, depending on the percentage you're looking for. If you're asked to find something like 21%, it's not going to be easy to find that because you actually have to break your bar down into very, very small pieces. We're talking like 1% or 3% or 5%. That's going to be a lot of pieces to break your bar into, so this is why it's important to know both models. Let's take a look at example 3. A bag of candy contains 300 pieces, of which 28% are red. How many pieces are red? They've broken down our question into 2 parts. They ask us which of the terms in the percent equation is unknown. Define a letter variable to represent the unknown quantity. And this really follows what we've been talking about all year long, that anytime we have an unknown, we're going to use a let statement to define it. And then they ask us to write and solve an equation to find the unknown quantities. I definitely want to know some of the important pieces in this so I can identify my unknown. They tell us that a bag of candy contains 300 pieces, and of which 28% are red. The question asking how many pieces are red. So that really tells me what my unknown element should be. So we're going to say let X equal the number of red pieces. So if I'm going to write and solve an equation, instead of just translating, what I could also do is identify the percent, the part, and the whole in this problem. So notice it says a bag of candy contains 300 pieces. That means the entire bag. So this is going to be our whole. They tell us that 28% are red, so this is our percent. And when they want to know how many pieces are red, this is going to be our part. So I'm going to start with the formula we talked about in the beginning. Percent times whole is equal to part. So using this, I'm just going to substitute the values that I know. So for example, we know the percent is 28%, so as a decimal, that's 0.28. Times the whole. They did tell us the whole is 300, so let's replace whole with 300. Is equal to the part. We identified that as our variable x. So again, there's nothing to really solve here. We just need to simplify by multiplying 0.28 times 300, and that gives us a value of 84. So to answer our worded problem here, there are 84 red pieces of candy. Let's take a look at two more examples involving word problems. Example 4 says Zoe inflated 24 balloons for decorations at the middle school dance. If Zoe inflated 15% of the balloons that are inflated for the dance, how many balloons are there in total? Solve the problem using the percent formula and verify your answer using a visual model. So if I'm going to use the percent formula, I need to identify some important pieces like the percent, the whole, and the part. So it says Zoe inflated 24 balloons for decorations at the middle school dance. If Zoe inflated 15% of the balloons that are inflated for the dance, how many balloons are there in total? So the different pieces of this tell me that the 24 balloons that Zoe did is part of the whole. The 15% gives me my percentage here. And this tells us that our unknown piece here, how many balloons there are, is going to be our whole. So we need to define that. Let's let X equal the total balloons. So if I'm going to use percent times whole equals part, we're just going to substitute. Our percentage we found was 15%, so as a decimal that's 0.15 times whole. In this case, our whole is our X value, is equal to part, in this case is 24 balloons that Zoe inflated. So if I solve this equation, I have multiplication between the 0.15 and the X, so we want to solve, we're going to do the opposite operation, which is to divide. And if I do it to one side, I have to do it to the other side. 15% cancels on the top and bottom here, and we're left with X equals 160 balloons. We are then asked to verify our answer using a visual model. So I'm going to use a bar model here. Now I know that the value of the entire bar is going to represent our whole, which is X at this point. And we were told that Zoe inflated 15% of the balloons. So I really want to break my whole into as many 15% as I can. So if we do 100 divided by 15, we get a whole number of 6 with a remainder. So I'm going to first start by breaking this up into 6 pieces to represent 15% each. So each one of these is going to represent 15%. And if I add those all up, what I end up with is 90%. And so this last one here is going to represent 10%. So we kind of have to find a way to figure out what each of these boxes is going to be worth. So each of these are 15%. So we know that 15% represents 24 balloons. So because each of these boxes represents 15%, each one of these is 24, except for our last box, which represents 10%. Now, there's a way to figure out what our 10% is going to be. What I'd start with is take the idea that if we look at 15% and we wanted to turn it into 10%, 10% would be equal to 15% being divided into 3 parts, which would give us 5% each. And then we want 10%, so we'd multiply by 2. So I'm going to take that same concept and apply it to what the value of 15% is, which is 24. So we're going to take 24 divided by 3 and then multiply by 2, and that gives us a value of 16. So that tells me this last block here is 16. If I add all of these up, all the 24s and the 16, we get a grand total of 160. So this verifies our conclusion that there are 160 balloons total inflated for the dance. Example 5 says Haley is making admission tickets to the middle school dance. So far, she has made 112 tickets. Her plan is to make 320 tickets. What percent of the admission tickets has Haley produced so far? Solve the problem using the percent formula and verify your answer using a visual model. So we're asked to use the percent formula. So we would definitely want to use percent times whole equals part. So we need to know some of the elements in this. Let's go through and highlight some important information. So far, she has made 112 tickets. That's going to serve as our part. And the plan is to make 320 tickets total, so that's going to serve as our whole. The one thing I do not know here is the percentage, so let's let X equal the percent produced so far. So if I go ahead and substitute, our percentage for now is going to be known as X. The whole, we are told, is 320. And the part, we are told, is 112. So I need to solve for X. This is multiplication, so I would divide both sides by 320. 320s cancel over here, and we're left with X equals 0.35. And so when I turn that into a percent, we will find that Haley has completed 35%. In this lesson, you have learned that percent means per 100. So P percent is the same as P divided by 100. Usually there are 3 ways to write a number: a percent, a fraction, and a decimal. Fractions and decimals are related to the ratio of the percent over 100. Visual models or numeric methods can be used to solve percent problems, and we saw examples for each. Equations can be used to solve percent problems using the basic equation percent times whole equals part.